Recording. All right, so if you have like any particular question about like specific homework problem or like class materials, you can raise the question. Or otherwise, I would say, basically talk about each homework question in in not a very deep sense, just by order. Is that okay? Like we have 7 questions this week. Okay, so you said question 5 specifically. Okay, I will do that. Actually, I will talk about question 5 first. Any other questions specifically that maybe you think it's really tough? Five and seven, all right? Okay, so for question 5, that's a question about binomial distribution. But here we can apply like central limit theorem to do it. As you see, like you have 1000 tokens. That's absolutely a very huge number, um, which gives us like allows us to utilize the central limit theorem. But first, we have the distribution of x, we have the distribution of y, and the question is how do we find the distribution of x minus y, right? So x follows a binomial distribution with 1000, n equals 1000, that's the number of tokens we have, and p equals q equals 1/2. That is your probability of getting a head or a tail from a single token. And from the class, right, so basically the three important, maybe actually two important parameter of the binomial distribution is your n and your p and also your q. But since this is a binomial distribution, if you have your probability of success, then you use one minus p, and that's your probability of failure, right? You can define like maybe head equals to success and tail equals to failure, right? Anything you want. Um, but MPQ are three important parameters in the binomial distribution. Here you have them all: n equals 1000, p and q equals 1/2. So you can calculate anything you want, right? For example, the standard deviation, the variance. I think you have a formula like the square root of MPQ, if I remember correctly. So you use the square root of 1000 times a half times a half. That's your standard deviation. Now the question is, what's the distribution of x minus y? So basically, x has an expected value of 500. Is that okay, right? You're tossing 1000 times with a probability of a half, uh, resulting in heads. So you expect 500 heads. And the same applies to y. Their expected value is 500. And I think you learned this formula in class, like expected value of a minus b parenthesis. For example, in this case, the expected value of the parenthesis of x minus y equals to the expected value of x minus the expected value of y. And the same applies to plus, right? You can have either plus or minus here. So here the random variable, if we look at x minus y as a whole, it has an expected value of 500 minus 500, which is 0. So yeah, it's true. It's true. Yeah, Carolina, that is the formula I mentioned. But in order to utilize like central limit theorem, remember your central limit theorem, the formula is z equals to I think the number x, that's the number which is given in the prompt, which in this case is 50, like z equals x divided by the standard deviation of the random variable. That's the formula of your z-score, right? If you have reviewed the central limit theorem. And here we just calculated the expected value of the random variable of x minus y. But what we need is a standard deviation of x minus y. And that's also not very hard to do it because we have everything needed for x and y. Now we just want to minus those two, right? And here we're gonna utilize another formula, which is the variance of a plus b or a minus b is simply the variance of a plus the variance of b minus maybe 2, I think 2 times the covariance of a and b. That's how you like plus or minus the variance. That's the way you do it. But here, one good thing is x and y are independent of each other. That means the covariance equals 0. The last term, the covariance term, equals 0. Like covariance is like a tools to measure co-movements. In reality, I think in finance, when you want to study like different stocks, they probably have a very high covariance or co-movements. Like if S&P 500 goes up, then a lot of stock just go up. Like if the price of gold goes up, then it's very likely the price of silver would also go up. So that implies a large co-movement. And in that case, you should be very careful about the covariance term because that's not going to equal 0. But here, x and y are independent of each other. Like I first chose 1,000 coins and I have my x variable. And then I chose 1,000 coins or I chose that one coin 1,000 times. The result of the second 1,000 chosen is independent from the history, is independent from what happens when I chose like first 10,000, like first 1,000 times. So x and y are independent from each other, and the covariance term is 0. So in this case, the variance of the random variable parenthesis x minus y should equal to the variance of x plus the variance of y. And that's how you do it.
Could you repeat that last equation, please?
The last equation is when you have two random variables, a and b, given that a and b are independent of each other, then the variance of a minus b or a plus b, they are actually the same in terms of variance. The variance of x minus y in this case equals to the variance of x plus the variance of y. That's the last formula I'm using.
Thank you.
But that is only true for independent random variables, right?
Yeah, exactly. And as I mentioned, if x and y are not independent, then you should add a covariance term after the formula I just mentioned. But in this homework, I think in an exam, you only have like independent cases. And in reality, you have some dependent cases, like my example of stock co-movements. But actually, you do also have some independent cases like your toast coins. So it's not in a sense meaningless, but in various cases we don't have covariance, or maybe the covariance is small, like we know the covariance is small, they kind of maybe they have some relationship, but it's small and difficult to measure. So in that case, maybe we just assume there's no co-movement at all and we don't use that covariance term. So that actually is very useful in real life.
Okay, thank you. And one more question. Why is the variance of parentheses x plus y the same as the variance of parentheses x minus y?
Because the variance measures like fluctuation. For expected value, of course, the sign matters a lot. But for variance, it measures fluctuation. You can think of in this way, like uh, a stock, it could either the price of the stock could either go up, could go down. Um, but like if it goes up a lot, we say it fluctuates a lot and the variance would be high. If it goes down a lot, we also say it fluctuates a lot and the variance would be high. So that's the like the intuition.
Oh, okay, thank you. So it's basically in absolute terms, that's why.
Yes, that is right.
Okay, thank you.
So then it just asks you what's the probability of x minus y exceeding 50, and you know how to do it using like central limit theorem. The z-score is just 50 divided by, I think, the standard deviation of x minus y, and you have your calculated z-score. Then you look at the table and like you find the cutoff 5%, I think. That's how you do it. You can actually find, but here it asks you to find the probability, so you should like come you should find, I think you should find the closest z-score uh, at the table, and then the corresponding probability would be the answer for this question. So move to question 7.
Yes.
So this is a simple application of conditional probability. I think this is very important. You should anticipate like similar question in your midterm exam. I think you had a quiz or not, I don't know. I didn't grade that. Um, but I think you should anticipate a similar question in midterm or final, which I will grade. Um, the basic formula, like, and by the way, you can prove that just using a simple Venn diagram. The basic formula of the conditional probability is like the probability of A given B equals to the probability of A intersection B divided by the probability of B. And you can transform that formula a little bit. So here you are asked to calculate the probability of heads given that a white ball was selected. So here your event A is gain a head, and your event B is the white ball was selected. And you know that the probability of that conditional probability equals to the probability of head and white divided by the probability of white. So let's do this in two parts. We have a denominator, we have a numerator. The denominator is the probability of white. And the numerator is the probability of head intersect white. We could transform our numerator a little bit. What's the probability of head and white? We could apply this formula again. And you should remember that actually the probability of A intersect B is actually the probability of B given A times the probability of A. That's another formula that you should remember. I think maybe I can type here. I think it's not very easy for me to type here because I have to look at the question. So maybe you can just bring like a piece of paper or something and to write them down. So the two very important formula is first the probability of A given B equals to the probability of A intersection B divided by the probability of B. And we can use this formula again and we would get the second formula, the probability of A intersection B equals to the probability of B given A times the probability of A. The second formula actually is derived from the first formula. So here we can transform our question to the numerator is the probability of white given head times the probability of head, and the denominator is the probability of white. So I just like decomposite this question into three parts. First, I need to calculate what is the probability of white given head, which means I already toss the coin and appears a head. Then what's the probability of getting a white ball? That's the first part. Then I times the probability of head, which is very simple, it's just 1/2, and then divided by the probability of white. These three parts are all easy to calculate, right? First, the probability of white given head, it's easy to do it because you have your head and you know which pole to draw the balls. And then you times the probability of head, which is simple, it's just 1/2, divided by the probability of white. This is like the probability of white is a little bit complicated to do, right? Because you have two situations. The probability of white equals to I toss a head and then draw a white ball, plus the probability of I first toss a coin and get a tail, and then I draw the white ball. So in the denominator, you should also like decomposite the probability of white ball into two parts, which is first the probability of white ball given a head appears, plus the probability of white balls given a tail appears. And that's basically the idea of how you do this question. For question number 6, actually you use exactly the same idea. So I won't be talking about question 6. But this question, as I mentioned, is important. You should, like, I highly recommend you to like maybe like this time you followed my instructions, you followed my steps, but like after, like before exam, I think you should do this question again by yourself to see if you really like understand the concept of conditional probability. All right, so then I will talk about some basic ideas for the rest homework problems. Okay. The first one, that the two deals are independent. So basically, if the two deals are independent, then the result of the second deal is independent from the result of the first deal. Like no matter what is my outcome of my first deal, my outcome of the second deal doesn't change. And here I think a basic counterexample is, for example, you draw your first card, maybe that's a king, and then if that happens, then the probability of drawing a king in the second deal would decrease because you have, like, there's only 3 kings in your deck. You already draw out 1 king in the first deal. And so basically the outcome of the second deal is dependent on what happened from the first deal. For example, if the first deal, instead of drawing out a king, I draw out a queen, then the probability of draw out another queen from the second deal would decrease. So that means it's not independent. But like in your write-up, you should like write it more clearly. I just provide some basic ideas. And you should follow like exactly the same step for question 2. You just like logically you just think about whether the outcome of the first decision would impact the outcome of the second or the third. and if mutually they do not impact one or each other, then all those events are independent. But that's more of a qualitative analysis. And for question 3, we would apply like a more quantitative analysis of independence, uh, where like a very famous formula to test independence is whether the probability of A intersection B equals the probability of A times the probability of B. So today we have a lot of formulas related to probability. Right, if two events are independent, then the intersection of those two events has a probability of the probability of A times the probability of B. In this case, what you're gonna do is you will first find the probability of the failure of element 1, and then you find the probability of the failure of element 2, and then you find the probability that element 1 and 2 both fail, right? So you basically you have the probability of A intersection B, which is in this case the probability 1 and 2 both fail, and you have the probability of A alone, which is the probability that element 1 fail, no matter what happens to element 2. And then you have your probability B, which is the probability that element 2 fail, no matter what happens for element 1. And you plug in your number into that equation to see if that equation holds. In reality, the equation never holds because here you just do some simulation, you do some experiment. But if that equation is very close to be held, then you have enough evidence to show independence. And for question 4, we use exactly the same idea as question 5. We use a z-score. Here you may argue that your sample size is not huge enough, like you only have 10 independent random variables. And is that legitimate to use central limit theorem? I would say yes, right? In reality, when you have like a uniform distribution or like exponential distribution sort of thing, then if you add 10 of them together, the resulting distribution is very close to the uniform distribution. There's some other more weird distribution when they like converge to uniform distribution a little bit more slowly. But for this one, the uniform distribution, when you have 10 of them, it's very safe to use central limit theorem, which is to approximate your resulting distribution to a bell curve, to a uniform distribution. So here you have like exactly the same problem as question 5. Now you have 10 independent random variables and you're summing them up together. So your ending distribution, your resulting distribution is actually the sum of 10 independent distribution. And for each distribution, because they're uniform distribution, so for each distribution, you have a mean of 0.5. It's uniform distributed over 0 and 1, which means equal chance everywhere. So your expected value is just the middle point of 0 and 1, which is 0.5. And you add 10 of them together, your resulting distribution would have an expected value of 0.5 times 10, which is 5. And you have your expected value, but what's more important is your variance or standard deviation. So just like x and y in question 5, here you have 10 different, maybe 10 independent uniform distribution, and you can calculate the variance or the standard deviation of each of them. You're going to use the formula of a minus b squared divided by 12. I don't know if that covered in the class, but for uniform distribution, the you have the variance which equals to a minus b squared divided by 12, and a and b are just two ends of your distribution. In this case, it's 0 and 1. That's the two extreme value that you can get. So you have your variance or standard deviation of independent uniform distribution, but you have 10 of them and you have to sum them up. So you're going to use exactly the same formula as in question 5. The variance of a plus b is the variance of a plus the variance of b and plus some covariance term. In this case, you have a lot of covariance term because you're adding 10 distribution together. So x1 and x2 may have some covariance. x1 and x3 may have some covariance. x5 and x8 may have some covariance. You have a lot of covariance term, but very luckily here, like all the covariance term equals 0 in this case, because your 10 random variables are independent from each other. They all uniformly distributed over 0 and 1, but they're independent, right? The outcome of x1 do not affect the outcome of x2 or x3 all the way to x10. They're independent of each other. So here, like you can simplify your covariance term to 0, and the variance of a plus b plus c, right, just equals to the variance of a plus the variance of b plus the variance of c, etc. And here you have identical distribution. So basically you just multiply your variance you just calculated by 10, and you're gonna get the the variance of the resulting distribution. And after that, you follow the same step of calculating your z-score. I think I made a mistake. You raised a very good question. Wait a second. Oh yeah, I didn't review statistics for long, so I made a horrible mistake. I said uniform distribution. No, I really mean normal distribution, the bell curve. So the central limit theorem states that for a lot of distribution, if your sample size is big enough, you add them together a lot of times, then the ending distribution or the resulting distribution would converge to a normal distribution or a bell curve. And the z-score is where you can use when you have a normal distribution, right? The z-score is just because a normal distribution has a very ugly probability density function, like e to the like x squared divided by 2, something like that, and it's not really differentiable. Oh, I think it's differentiable. It's not really integratable. So you cannot use calculus to find like the area behind that curve. Cannot do that. What you can do is you do some simulation and you cut the area beside that curve into infinitely many rectangles or trapezoids, and you add those areas together. You find the area. Basically, the area should add up to 1, but your z-score, right? Remember that 1 means when your z-score is from negative infinity to positive infinity, then your area should be 1. But what if I give you like a specific z-score, maybe 2.5 or something? Then you cannot use calculus tools to find the area on the right of 2.5 or on the left of 2.5. We know the area on the right of 0 should be 1/2, and on the left of 0 should also be 1/2 because the bell curve or the normal distribution is symmetric. But if I give you an arbitrary number of z-score, for example 2.5, then you cannot solve it. So what we're gonna do is we're gonna cut that bell curve, that shape, into infinitely many parts, and we use computer to calculate the area with small errors, because it's just simulation. You cut it infinitely many times. In theory, you would get a correct number, but in reality, you cannot cut it infinitely many times. You can cut it 10,000 times, you can cut it 100,000 times, but it's not infinity. So you have some errors. And statistician, they did that. They use computer to do that, and they get their result, and they write down their results into a table, which is your z-score table. So if I give you a z-score, which is 1.65, with some remainings, right? If I said my z-score is 1.65, then you can look at your z-score table. I think there's one number exactly equals to 1.65, and you can find the probability, which is the corresponding area on the right or on the left of that z-score. So that means you have to first have a normal distribution to use the z-score. It's only legitimate to use your z-score formula when you have a normal distribution. But in this question, what you have is not a normal distribution, it's a uniform distribution. But you have 10 independent, identical uniform distribution, and when you sum them up, the central limit theorem tells you your resulting distribution or your ending distribution is very close to a normal distribution, because you're adding 10 uniform distribution together, and that's pretty large. So uniform. So basically, central limit theorem and z-score formula, they are two different things. Central limit theorem is a theorem that tells you when you add many weird distribution for a large number of times, then your ending distribution would approximate to a normal distribution. That's what central limit theorem tells you. And the z-score formula tells you if you have a normal distribution, then you can use the z-score to calculate the probability in a very efficient way. So here, the logic of this question is, first, I don't know nothing. I have 10 uniform distribution, but when I add them up, the central limit theorem tells me my resulting distribution would be a bell curve, would be a normal distribution. And that grants me to use the z-score formula. That's the step of this question. Was a very good question. Thank you. Any other questions?
Hi, I have a question about number six. It's just like how, kind of, six and five, but just six first. Actually, five, six, and seven, but six is it like would it be the way to solve it? Just the probability of uh, it's basically conditional probability of like probability of choosing French, given that it is Californian, or is that not the correct way to solve it for this question?
Yeah, the setup for this question would be what's the probability that the California wine was served given 4 out of 5 judges guess it's French.
So it's
That's
the
the
opposite.
setup. Sorry?
Is the opposite setup like probability uh, of getting Californian, considering that they chose French.
Yeah, I think so. Because the probability of A given B, right? Remember that B is known, and you want to find what's the probability of A given something known. Here we have like there's a fact that 4 out of 5 judges guess this wine to be French. That's something given. That's a fact. So basically, I'm calculating the probability of this wine is California given 4 out of 5 judges guess it's French.
Oh, okay, got it. And for seven, is it okay if I like the chances I sum up the chances of white balls and black balls appearing, or like I just add up like all the
Yeah,
total
I
balls?
went through this question before. First, I would I will like upload this recording as soon as possible, maybe just in 1 hour, like because YouTube has some I don't know checking process. Um, but I knew like you have already done this question, so I think you could like follow up my pace. So here the question is I'm gonna calculate the probability of head given white. That's the setup of this question. And if we use the Bayes formula, the probability of A given B equals the probability of A intersection B divided by the probability of B. So we can rewrite this question into the probability of head intersection white divided by the probability of white. That's the second step. And then we're going to transform the numerator part, right? The probability of tossing a head intersection, the intersection like a white ball is choosing. So that we're gonna use like another formula, which is probability of A intersection B equals to the probability of B given A times the probability of A. So we use this formula to transform the numerator part, and we get our maybe the final setup of this question, which I can write this question as the probability of white given head times the probability of head divided by the probability of white. And I can calculate those three probabilities very easily. Right, the probability of white given head is easy to calculate because as I said, head is known here. It's given head. So I know I toast the head and I know like which containers to find the ball. So I can calculate the probability of a white ball very easily. Then I times the probability of head, which is also easy, it's just 1/2, and divide it by the probability of white ball. Here is just a denominator. The probability of white ball is a little bit complicated to calculate because you should divide that into two parts. The probability of white ball given I toast a tail plus the probability of the white ball given I toast a head. So basically you just play with the Bayes formula like many times to make your to make each probability easier to calculate. And basically you're gonna use exactly the same idea for question 6. They are basically the same.
Okay, perfect. The same idea as 6, which is the. Oh, okay, perfect. Good. And did you go over number 5 or?
Yeah, I did. I walk you through like some basic formula. But if you want to like know exactly the whole step, you can watch the recording. It's on the I think it's on the first half of the recording. So x and y are random variables following a binomial distribution. And what I need to know is what's the expected value of x minus y as a whole as a random variable, and what's the variance or standard deviation of it. So what I have here is everything about x and y, because x and y follows a binomial distribution, and 3 important parameters about binomial distribution is NP and Q. Is the number of toasting you have, which is 1000, is given here. P is a probability of success. Here you can understand that as a probability of getting ahead, which is 1/2. And Q is also 1/2, the probability of getting a tail. So you have N, you have P, you have Q. And I think from your class you learned the standard deviation of this binomial distribution is simply the square root of NPQ. The square root of 1000 times a half times a half. That's your standard deviation. And you square that to have your variance. Now, we could first calculate the expected value of x minus y, which is using a formula, the expected value of a minus b as a whole equals to the expected value of a minus the expected value of b. So here your expected number of x is 500 because it toast 1000 times with a probability 1/2 to success to get ahead. So the expected value of x is 500, and the same applies to the random variable y. It's also 500. So the expected value of x minus y as a whole is 500 minus 500, which is 0. That's the expected value of your new random variable x minus y, which I can actually substitute that into z. Let's suppose z equals x minus y, right? So the expected value of z is 0. And what's the variance of z, right? You're going to use another formula like the variance of a plus b or a minus b equals to the variance of a plus the variance of b minus some covariance term in the end. And here, because x and y are independent from each other, so the covariance equals 0. So here, the variance of z, or the variance of like x minus y, simply equals to the variance of x plus the variance of y, which is, I think, is MPQ plus MPQ. That's the variance of your new random variable z. And then you could apply the z-score formula, like z equals to x minus mu divided by the standard deviation. The standard deviation is just the square root of the variance you just calculated, and x minus mu in the numerator is 50 minus 0, right? Remember, mu is just your expected value. Expected value of your z variable is 0, and x minus mu, right? X is something you want to find. In this case, it's 50, given in the prompt. And that's the whole process of this question. And by the way, for question 4, you use exactly the same idea. I just mentioned it. But here, your z-score x minus mu divided by the standard deviation, your x equals 7 in this case, right? That's something you want to find. But mu doesn't equal 0 in question 4. Mu equals 5, right? Because that's your expected value of your new variable. You sum in 10 uniform distribution together, each with an expected value of 0.5, and you sum 10 of them together, and that results to the final expected value of 5. So when you use your z-score formula in the numerator, you should write like 7 minus 5 instead of 7 minus 0. That's x minus mu. That's a common mistake that many students have went through.
Okay, I got it. I think I'm gonna go back in the recording just because it's like a lot of very lengthy process. But wouldn't the mu be 5.5 there? Just I'm really confused.
Sorry, my volume is not very big. Can you say that again?
Isn't the mu 5.5 on number 4?
For question 4, mu equals 5.
Oh, 5? Okay.
Yeah, because like the uniform distribution means there's equal chance everywhere. So if you have one uniform distribution over 0 and 1, then your expected number is just in the middle. It's just a half. That's
Oh,
your
I see.
expected value for one uniform distribution. And here you have 10. You're going to sum them up. So the mu equals 5 in this question.
Okay then. Thank you.
Wait, there's
I
a
think that was
baker on
all.
fire?
For next week homework, I didn't look at it. I think I can do it right now, maybe. I'll stop recording, right? I